as you see this background setup here, let me explain what's happening here. Well, in the comments regarding fuel percentage, I've read several comments that said, well, Blackstone's oil percentage is off, another company's is more accurate, so on and so forth. However, technically, you really don't know which one is right. So the only way to figure out how accurate a system is to actually pressure test that system unless you have a gold standard to compare that against. I don't have a gold standard to compare Blackstone's fuel percentage against, but what I can do is that I can submit multiple samples that have a known amount of gasoline inside the oil. And then therefore, if they come back with accurate results, we can say that their results are accurate. And if they come back and they're inaccurate, well, we can say that they're inaccurate. One quick thing I do notice that they use, let me see what the, let me get my phone out real quick. I'll tell you the method that they use. They use the STM D92 for the flash point. And then from the flash point, they actually derive the fuel percentage. So basically what they're saying is that every 20 degrees below the flash point should translate to 1% fuel dilution. Okay, so all well and good. So they're using sort of an indirect method versus some other places might use an actual direct method to actually measure the actual gasoline molecules present in a given volume. So how are we going to test this system to see just how accurate it is? Well, what we're going to do, we're going to test the accuracy of their results that they generated Blackstone Labs by a method called dilution or linearity. So basically, what we're going to do is we're going to add enough oil in here and then add a known amount, which I'm going to begin with 12% oil in this first one. Then what I'm going to do is I'm going to cut it in half and go to the next one. That's going to make 6%. For this one here, I'm going to cut it in half. And this is what you call a 2x dilution. And that's going to be 3% in this one. Then I'm going to do the same 2x dilution to this one. And then in this graduated cylinder here, we will end up with 1.5%. Now, why did I choose to do serial dilution versus independent, what you call spikes? This is what you call spiking in the first one. It's because if you look at these beakers, I don't have any really expensive, these graduated cylinders, they're not really that expensive, so they do have a small amount of error, about a 2% spread, about 1% plus or minus at the max volume here. So we're gonna fill this up to the max volume here to mitigate that small amount of error. And if you do dilution or linearity, basically it's all relative. Like in this beaker, in this flask, graduated cylinder will have half of what this have. This one should have half of what this have. This one should have half of what this had. The values may not be all that accurate necessarily, though they could be. Who knows? That's what we're trying to figure out. But the thing is, you will have less pronounced error if there's some error in this system right here with these very inexpensive graduated cylinders here. So we have everything marked. And one last thing I want to say is that I'm going to take the plain base, this right here is what you call, I'm going to submit a sample to oil with no known added gasoline to it. And that's going to be what you're going to call the baseline. Now, this video here is going to be in 3 parts. This part here is just going to show this how I'm going to spike the samples and then collect the samples to ship them out. The second part is going to be a little bit more in depth of what exactly is going on here and how this system here is going to can effectively pressure test their method for robustness. And the third part is going to be the results. So this video will be time-stamped, so you can feel free to go to the part in the video. And what I'm going to do is I'm going to spike this first one here. We're going to walk through this one. And then I'm just going to speed the video up for these right here, because all I'm going to go be is diluting 2x here, and then 2x from that one, and 2x from that one to here. And then we're going to package these samples up over here and ship them out to Blackstone and see what happens. But again, I'm not telling them that and I will, for full disclosure, I did communicate with the company to tell them that I would be sending these samples in, but this video will come out after I get the results, and they will not know exactly how much I'm putting in each one to submit. So there you have that. All right, so what we're gonna do here is we're gonna go ahead and fill this first Well, actually, let's do something first before, let's be a little thorough here. Since this right here is sample, this right here is sample, I don't know if you can read that, 1 of 5. We're gonna go ahead and add just our baseline in this right here. So that's gonna be just a plain oil. That's not saying that there's no gasoline in here, by the way. I wanna make that clear. It's just saying that we're not adding a known amount. Now let's just say, if there's a little bit of gas in here and it detects it, you can subtract this amount of gas from the rest of the samples that you get, and then that will correct for that. So let's go ahead and get us a little sample here to ship out to Blackstone, our baseline. Okay, not too bad. Put that up there. Next, we're gonna put this inside of the extra protection here. Bottle that up, and we'll do just one. Hold on, let me get the air out of there so this will fit properly. Okay, put that on in there, and just stuff that down in there and close that up. That is right there. That is the baseline sample here. All right, for this next sample here, I'm going to fill this up to 220 mLs of this used oil here. And again, much more in detail will be explained in the second part of the video about this oil, where it comes from, all of that. And much more will be explained about the gas in the second part of the video, but this is just the sample collection part. Again, we're just gonna put 220 mils of oil in number 2 here, and we're gonna add 30 milliliters of gas to that, and that's gonna make 12% gas. And then we're gonna set that here on the stir plate and stir that up, and that will mix that up thoroughly. And then we will just cut this in half, take 125 mLs from here, add it to here, to 125 mLs of oil with no gas, and keep doing that until we get down from 12%, 6%, 3%, 1.5%. Okay, let's go. 220 mils. So what I'm gonna do is I'm gonna get it close. We're just pouring it in here like this. Then I'm gonna take a transfer pipette and refine this. Let's get a little close. Getting closer. Okay, that's a little close. So now what I'm gonna do is I'm gonna take my transfer pipette here, and I'm going to just transfer that some over so I can get that exact, well, close as it can on 220 mils. And again, you may start to see why I'm doing dilution or linearity now, because if any errors in the system, this will, sort of wouldn't say overcome that, but it's more easy to correct for this, because again, each sample is relative to the next sample. Okay. And because technically we're probably dealing with such a very large percentage of gas, I mean, relative to the amount, because for example, 1% gas should be 2.5 mils of gas in this beaker. That's actually a good amount. So we're still refining this, getting close as we can. Getting close as we can to 220. Let's see. Yeah, that's right on 220 there. Okay, so let's set that to the side here. So now let me get a little bit of gas here. I have not poured the gas out yet because I didn't want the fumes just floating around. I do have my garage cracked and 2 fans ventilating my garage as well. So yeah, so there you have that. I went and bought this little press and pour can right here. So it's supposed to be pretty cool. It's supposed to just be able to press this down, press forward and press it down. I haven't poured gas out of a can in years. So this is all new to me, because gas funnels, the little ends didn't used to look like this here. Okay, so is that 30 mils or close to it? Actually, it's not quite 30 mils. Let's pull a little extra here. Let me see, all right. Again, if I'm being awkward pouring this, it's because, again, these new systems are not like they used to be. If you've been around for a while, you know what I'm saying. This is something totally new here. It used to be you almost could just take the top off and just pour it right out, and that's it. So anyway, this here is the same gas that I use in my truck, which is 89 octane from BP. All right, let's go ahead and fill this up to 250 mils here. I'm gonna go ahead and let me do it this way here so you can see what's happening in real time. I'm gonna try to lean this and pour it first and get it close, then I'll refine it. Okay, that's pretty close there. We won't be needing any more gas after this here, because all the gas we need is already in this sample here. Put a little bit more, just a little bit more. All right, that should be 12, maybe just a tad more. I know these things ain't all that accurate, but I want to be as accurate as I can. Okay, there we go. That should be 12.5% gas. Let me get rid of this gas out of my face real quick. I'm gonna pour it back in this can right quick and set that cup outside because I don't want those fumes in here. So let me just pour this little bit back in here. Okay, then let me close this can up. Just want to get these fumes out of here because I don't need the gas fumes just sitting right in my face here. Okay, now just let me go set this right here, right over here outside. Just set that right there so it'll just be out of the way. Okay, now this right here is our starting point, 12.5% gas. So we're gonna set this right here on the stir plate. Now we're gonna take a stir bar, take a little stir bar, a magnetic stir bar, and just drop that right in there. Let that hit the bottom, and then we're gonna stir this up. And the idea is that I wanna let this, let me make sure it's stirring here. So that oil is kind of thick. And if I think that is not, I got a backup plan here. If that oil is too thick for this relatively weak stir plate that I bought for like $25 off Amazon, I did buy a pack of paraffin. And what I could do is just cover up the top really well and just invert it a few times as well if I need to do that. So what I'm gonna do is I'm just gonna let this probably, let me make sure everything is spinning here. Make sure it's spinning. I want to make sure I see a little vortex in there. Because again, that oil is very thick and probably not like water or anything that you might use in a chemical lab. Let's see. Give it a second here. It might take a second if it will reach the top, because again, if it does not, again, like I said, I have paraffin and I can just invert it several times and mix it well. Matter of fact, hold on, let me make sure this, let me. Okay, that's, let me see, let me make sure. Yeah, because the stir plate might just not be powerful enough for how thick this oil is. Let's see. No, max settings. Turn it back down for a second here. Okay, well this here, I don't see a vortex, so to me it's suggesting that it's actually not being able to spin this oil here. So what I'm gonna do, and that's okay, that's exactly why I bought this paraffin here for a backup here, and I'll show you how this works. All we're gonna do is, paraffin is a lab, basic general lab supply, and you can cover up things with it and it can make sort of an airtight seal, and then that way you can invert it probably 6 or 9 times. When I invert stuff like the specialty bag, I probably want to do it 3 times 3, which is 9. So I'll probably invert it 9 good times, and then we'll move on to the next container here. So let's do that. Since it appears that this is not spinning it. So, because again, I didn't think it was going to spin it because it's so, this is only a $25 stir plate, and this oil is kind of, and you might need a bigger column here with a bigger stir bar to stir it. So just may not be that. So what we'll do, paraffin, just stretch it out real good, and we'll make sure we got a nice tight seal around this top here. And what you do is you just make sure everything, spin it up there real good like so. Then you want to take your hand and just press on that, and then you can just invert it several times like this. Just make sure that everything is nice and inverted. How many times is that? I think that I'll just count 4. I count this as 5 because I can't keep up. 6, 7, 8, 9. I'll do 3 more. just to make sure. Okay, that should be thoroughly mixed, inverted up and down. Okay, because don't forget, regardless, what's ever in here will be relative to the next one. So let's take this off right here. I got a little oil on my glove here. And so what I'll do is, since y'all already know the concept, I'll quit talking now, and I'll just go ahead and do the rest of these, and I'll speed this part of the video up. And if there's something else I need to stop and talk about, I will, but I'll do it just for entertainment purposes. So there you have it. One quick note, I will just go ahead and reuse this because this, even though this already has a little bit of clean oil in it, it's not going to hurt just to stick it into this right here and transfer just a little bit over. So I just want to point that out real quick. Okay. what you guys just saw me do right here, I just put a little bit of oil in this cup and I'm just rinsing this out with the clean oil so I can just keep using the same one here because I don't have any more of these transfer pipettes. But that if it would only have a very small effect, if any at all, and I doubt it would have any effect. So I'm just pointing that out that although this is you know, a scientific endeavor here, something like this right here is not going to hurt anything. Just a little bit. Okay. All right, so that's it, guys. So I'm gonna go ahead and put these right here in the respective bags right here, ship those off to Blackstone. And again, there'll be 3 parts of this video. The video is gonna be kind of long, but again, they'll be time stamped and you can just go to the respective part that you need to go to. All right, guys, so I'm making this part of the video here well after I have made the first part of this video. So anyway, I have sort of kept this little study here secret for quite some time, and I had to go over the data a little bit, and the video is time stamped again. I know I mentioned that probably early on in the video, but just know that if you want to see the actual results, just go right ahead. We're just going to talk about the actual motivation behind the study and some other aspects of the study you can see right here on the screen. So the first thing I want to talk about, what is the motivation behind this? Well, a lot of people, we had discussions about the fuel dilutions, because I mentioned that a few times in some of my oil analysis with the restore and protect. And a lot of people were saying how, questioning the accuracy of Blackstone's methodology of how they determine fuel percentages. And also some other people saying, oh, well, if you send it over here to this other company that does FTIR, you get a completely different number, like 3 times different. And FTIR is the way to go, so on and so forth. Now, with that being said, there's no gold standard here per se between any of these methods, whether it be the Cleveland Open Cup method, which we're going to talk about in a minute, or the FTIR method. So the way that you would figure out who's accurate or what is accurate is that you pressure test their method with known amounts of an analyte. In this case, it would be gasoline inside of engine oil. This is not the ideal way to do this, and the reason why I'm saying is because I use engine oil from my truck. I mean, you would probably do like submit virgin oil samples. Again, this is more of a proof of concept study, and this is just to say, hey, what happens if what happens if we spike gasoline into motor oil? Can we get a linear response? How does the numbers make sense? So that's sort of the motivation behind this. Now, one quick thing I'll say about FTIR before I move on here is that FTIR is not really comparable to the Cleveland Open Cup method, which is typical flashpoint testing. And why am I talking about FTIR versus flashpoint testing? Because after all, we're talking about percentage of fuel, right? Well, it turns out that fuel percentage is derived, if you didn't know, because I didn't know this before I done my research on this here, fuel percentage is derived from the flashpoint if you use the Cleveland Open Cup method. And that's exclusively what we're going to be talking about in this video, except for just a little bit. I may mention other methods like right now I'm talking about FTIR just a little bit, because it's the standard for flashpoint testing in this industry for engine oil. But anyway, back to the FTIR. You can't really compare FTIR and the Cleveland Open Cup method because, first of all, FTIR is looking at signatures of actual gasoline molecules on an atomic level. And if you're not familiar with what FTIR is, basically every atom or combination of atoms, such as molecules, they absorb light in a very unique way. So where they basically have a different signature and under infrared analysis. That's just a simplified version of it. Now with the Cleveland Open Cup method, well, you're going to have some subjectivity to it. It could be pressure, barometric pressure, operator skill, temperature ramp, how well the sample may be stirred or mixed before you actually put it into the plate. We're going to take a look at how Blackstone does that in a minute. So in other words, it's kind of comparing apples to oranges, because you're comparing one that's kind of based on sort of, again, the Cleveland Cup is sort of based on environmental properties when you do the test, but FTIR is basically looking at atoms. So in a nutshell. So not really comparable at all, in my opinion, because I've actually done FTIR analysis on some raw materials when I did a study at another company I worked at. We use it to validate. Basically, it's basically just an identity and a purity method. Because again, we was doing something with packing columns for protein separation, and we were validating all of our raw materials. We're doing a bench scale rather, scale down of a manufacturing process step. So anyway, let's get back here and let's get to talking about what happened here. All right. So anyways, we can see right here by the title, this here is a proof of concept study, meaning that all we're trying to do is say, can we get a response that makes sense? Can we get something out of this before we do more research? And, in real research, sometimes you do what you call a proof of concept, or then maybe move on to maybe a feasibility, or say what you might call a pilot study before you really dive in. So proof of concept is just saying you're doing just enough to get some valid information, some good information that may make you make decisions on next steps. So that's what this here is. This could be done much more thoroughly than this, what I did here. But be it as it may, this is just what happened. I'm just a guy curious and want to share this on YouTube with his community. So this is what we have here. So what was the purpose here? Our purpose here, we wanted to assess the accuracy of fuel percentage measurements, Blackstone Labs. And I wanted to use what I call a controlled dilution or linearity study. And we'll talk about what that is in a minute. So basically the objective was that we wanted to see when we submitted oil samples with known amounts of fuel in them that was subjected to the Cleveland Open Cup method at Blackstone Labs, how much fuel percentage was they going to derive? Because basically Blackstone's laboratory's common practice is to say every 20% decrease of flashpoint correlates to approximately 1% of fuel contamination. Now, there's one caveat right there when you're talking about Cleveland Open Cup. Again, I got to backtrack a little bit to the FTIR, is that when you get this data, you have to take it into context. So let's just say if you check the flashpoint and it decreased, say, 100 degrees, but the viscosity did not change at all, that'll be different than if the viscosity also decreased as well. And we'll talk about it a little bit more when we actually look at the data here. All right. So anyway, I corresponded with Blackstone, and that's where I got this information here from. And so basically the questions that came up to me was, is the established, 1% of fuel contamination for every 20 degrees F, is that accurate? Or does that sort of correction factor or multiply could be refined? And also is the current baseline, because here you see where it says they use a standard baseline of 385 degrees. But however, there is much more or other ways you can, sort of refine it, such as using the SDS and see what they say, what is the minimum flash point, and kind of use that value as the should be standard value versus 385. So these two questions popped in my mind. Now, whether these need to be adjusted or not, I am not sure, but it's just something that was very interesting. And I hope that you also find this interesting. And so, what else I want to say? I moved on to, let's move on here to our, how we conducting this study. All right. So we just took used engine oil and we added some gas to it. And the same gas that I put in my truck is 89 gas from BP here in Apex, North Carolina. And I sourced the oil. It was about 3,000 miles on this oil out of my inline 5 from my 2006 Colorado. And basically, a serial dilution, or what I want to call a controlled dilution linearity, is basically I wanted to say do twofold dilution. So basically, based on the fact that if you say you got 20 and then cut that in half, and then you put 10%, cut that in half, and 5%, it's just logical to do that. And here's the table here if you want to read. I'm not going to really go through that, but the real logic behind why the rationale why I wanted to do serial dilution spiking was that I had some rather cheap, volumetric, I wouldn't say glassware, but just say labware that I bought from Amazon. And the accuracy of it, they said, was plus or minus 1%. The total volume of those graduated systems was 250 microliters, not microliters, milliliters. So that's 2.5, about plus or minus. So that's a 5 mil spread, if you think about it, plus or minus 2.5 mils. So this is beyond, normal tolerance. But for this study, it was okay because, again, this is a proof of concept. And also, if there's any defects in their volumetric markings, that the serial dilutions could be much more easily accounted for based on, each dilution having a relationship to one another. So that's how, that's the, the reason why I've done a serial dilution. Technically, to be much more thorough, you would prepare everything independently. And there's other scientific justifications for doing that we're not going to really get into. But I'll just say, again, for this right here, this is perfectly fine. And that's what we rolled with. So I've done everything right here in my house, right here in my garage, as I documented already, as you've seen earlier in the video. And so between the dates of testing here, I got February 13th here. That can't be right. I must have put the wrong. I'll correct this date, but basically, whatever date I collected these samples here, they got tested. Actually, this date here is probably wrong. I think I sampled these. This right here is probably the wrong date. I'll correct that date. Don't worry about that. And the longest time between sample collection and these samples, basically they wasn't sitting around. That's the whole point why you want to document the sample collection date and actual dates that they were tested. So there's that. So now, being that we went through just what the motivation is, how I carried it out, what questions we're trying to answer here. Let's go ahead and just look at a really quick video of how Blackstone actually does the Cleveland Open Cup method. But before we do that, I will say I will put this document here on Google Docs. If anybody's interested in reading it, you can use it however you want. If it's of any value to you, the only thing I ask you is you just don't change anything about it. And if you find any mistakes or anything in it or something that's questionable, just let me know. And if I need to amend anything, I will. But otherwise, there's that. So let me go ahead and open up this video here. So here we go. This right here, video, this is by Blackstone, and this is their flashpoint testing chamber. So let's go ahead and jump right into this.
Hello and welcome to the Flashpoint Chamber. My name is Joe, and I'm going to walk you through how we run a flashpoint test at Blackstone Laboratories. Here you can see the sample being pulled. We're going to drop it into the world's smallest hot tub, which happens to be a heated brass cup. We're going to insert the temperature probe, and then we're going to pay attention to a couple things. First of all, the temperature, which you can see being recorded right there, and then we're going to pay attention to when the flashpoint occurs, which is right now. This one we actually let go a little bit longer because you don't let a good visual go to waste, but it's the initial flash that we pay attention to. And then we discard the sample into our secret box, and that is the flashpoint test.
Very nice. I mean, I'm glad to actually put this online. This gives an actual visual of how this sample is tested and how you can surmise that, comparing this to FTIR with this super sophisticated instrument is not really a fair comparison. I mean, these instruments here are much more easily deployable. FTIR, for example, you probably had to have a service contract, have maybe a person or SME, which you call a subject matter expert, and consumables may be a factor. Again, like I said, I'm not an expert with FTIR. I have used it, but anyway, there is that. All right, so now, being that we've took a look at that, let's jump right to the results. This is what everybody's waiting for. So, all right. So first of all, let's scroll down. Again, I'm going to actually pull these data out and put these data inside of a spreadsheet. So I'm just going to really run through this right here in case if there's some people who just want to see this information and just leave, and that's totally fine. But I hope you watch the whole video, but either way. So, all right. So 0% fuel, of course, everything looks good in terms of flashpoint, viscosity, fuel dilution. At 12% fuel, we already see the first thing that this test here, the Cleveland Open Cup method, is limited up to 10% fuel. Beyond that, because why is that? I believe I didn't follow what Blackstone and asking this, but I think that before you actually start putting the fire to the engine oil and checking for the flashpoint, you have to ramp up the temperature. And I believe doing this ramp up to get it to, I think it's like 50 degrees below the expected flash point or something like that. That doing that ramp up is so much fuel that it might just boil or whatever, and therefore they can't complete testing, based on that protocol. So I believe that's what happened. So you get no result there. But I did kind of work around this and make a little bit of some sort of mock-up results, and we'll take a look at that. 6% fuel. Flashpoint dropped significantly, and they said 8% fuel, which is not that far on the surface. I mean, that's still okay. If you think about it, if you had 6% fuel in your 6% fuel in your engine, your car would likely be misfiring, smoking, or something. So if you had 6 or 8% fuel, it really wouldn't make that much of a difference at all in terms of what number did they report. Going down to 3% fuel, as you see, as we go down, they get a little bit closer based on their method. Here we got they reporting 3.5%. And I thought that was pretty good. And now we go over here to 1.5%. Now this is where things get a little tricky again. On the extreme ends, if you look here at the 12% and all the way down at the 1.5%, sometimes you get some outliers. And what I mean by that? Well, if you look here, this is 1.5% fuel, right? And this number should be greater than 385. And they said exactly 385, but they don't actually give us a result. They just say it's trace amounts. But now get this. Let me go ahead and flip over to my lacrosse real quick. This is my lacrosse. When I actually done analysis on this, they were able to surmise that I had 0.8% fuel. So again, 1.5 is higher. So they should have been able to calculate the 1.5. So in other words, what I'm saying is that you can see right now that this Cleveland Open Cup does have some variations, and it may be more impactful on very, very low amounts. So that's that one there. And also, let's go back to the CRV as well. If we look here, they were able to even actually detect 0.5. So basically, you can look at it like this. Every 5 degrees below flash point is 0.25% fuel dilution. So this way it was 10 below. So that's divided by 2. And then this here would be 0.5. So they were able to calculate that amount. But here, when I had 1.5%, it was only showing a trace amount. And now, in all honesty, let's look at it like this. If you had 1.5% fuel in your engine oil, it probably is not going to cause a problem. Now, I will say this. Let's just say if that was over a full oil drain interval, let's say 3, 4, 5,000 miles. Now, if you say done a 1,000 mile, oil analysis, and you had 1.5% fuel already at 1,000 miles, that could be a different story. So in other words, sometimes you need to take fuel dilution on a case-by-case basis. All right, so again, this is, I know that wasn't that quick, but this is going to be sort of quick compared to going over the actual graphs that I made here. But again, I'm just looking at the actual data so you can see that the actual raw data that I got from Blackstone was transferred over to my spreadsheet here in a minute. Something that's interesting is that look at the additive packages here, the molybdenum, calcium, magnesium, phosphorus, zinc. They all decreased. If you look at it going from the 0 to the 12, they all decrease. And it actually decreases with respect to fuel dilution. The only thing is that this sample that had 3% in it must have been done by a different analyst or something, because everything in this one is higher than the 6, and also higher than the 6% fuel, and also higher than the 1% fuel. But it's within, I would say, within tolerance. But the point remains is that the additive package can be affected by fuel dilution. However, it appears that the additive package is quite robust. So with that said, I just wanted to show you that. So let's jump over to my spreadsheet now and take a look at everything graphically, a little bit more in detail. So now if we look over here, first of all, don't worry about the plots just yet. Let's look at the tables here, because we got to go over a few things to kind of recenter ourselves here. Now, if you look at this additive packages, everything I got highlighted that's going from green into red. You see, if you look at 0% going up to, I put everything in order. That's another reason why I put it over here as well. It just persistently goes down, down, down for every single additive. So to me, this is a clear indication that if you look at all the relative error of everything, except for potassium, that's probably just one going from 1 to 0, just might be an artifact based on the assay, but that is persistent going from 3, 6, and 12. But anyway, everything has a negative bias to it, meaning that it went down. And by the way, I'm just using relative error here and sort of I wouldn't say it's an incorrect way, but I'm just using the 0 as the baseline. Usually relative error would be more towards a nominal amount that you might, for example, if I put, I don't know, 1,000 calcium here that I know what's in the sample, that then I would try to calculate a relative error based on that. But in this case, we're just going to use these numbers right here at the 0 time point as, say, the nominal, and then we will look at relative error from there. So again, we see that these packages do go down. I mean, this additive package everything goes down, in fact. And what do I think is happening here? Now think about it. What is gas? Gas is really, I'm talking about just the very basis of gas is just a bunch of hydrocarbons. So what do you think is happening here? So I got a theory here. I'm going to show you what I think is happening here. Let's flip over to my other sheet real quick. Now, if you look at this here, now this right here is all the Hofmeister scale. And they're talking, we're just going to pay attention to the bottom row here, which is the cations here. Now, if we look at sodium chloride, now anybody working in a biological lab, you didn't notice that sodium and calcium really, why they're using a lot of buffers in a biological lab, because again, once they go into solution, basically they end up with the same valence shell as the previous noble gas in the previous period. So they're quite inert. That's why they're using a lot of buffers, by the way. But again, if we look at these calcium, magnesium, and zinc, all these things are additive packages to oil. As they go up, they become, well, we're just going to say they're not really more reactive, so to speak. But that's what everybody says, and that's the practical way to say it. So we're going to say it, but it's not the real term. But anyway, calcium, magnesium, and zinc is much more reactive. Now, I just wanted to show you this right here because you can see, look at what it does. If you think about zinc, it sort of can, calcium, magnesium, and zinc, they sort of have more propensity to actually bind to the surface of the actual molecule versus forming a shell around it, which you see on this side over here, on the left side. Now, again, we're not really going to go into the lytropic properties of these cations here, but what I want to show you here on this next scale, which is the same scale, but I just want to point out that if you look at going towards green, these have very high propensity to solubilize hydrocarbons. So what do I think is happening here? Based on the levels of gasoline that's not being accounted for, as you'll see here in a minute, and the actual lowering of the of zinc, magnesium, calcium, and whatever, I think that's what's happening is that if we go look at this picture right here, put it more on a picturesque, is that if you think about it, it's more like if you look at these red spheres here, they are actually binding more around those hydrocarbons and sort of they're being more misrepresented, aka they're being counted as being lower than they really are in solution. So that's what I'm pretty sure is happening there. All right, so and let's see what else. Now let's scroll down to the actual gas. I mean, to the actual fuel percentage they calculated here. So now, based on Blackstone's numbers, this is what. Now, again, let me just give you the caveat here. And in 1.5%, they said trace. I just arbitrarily assigned it half of 1.5, since I just put 1.5 in it. There's just no way to know what it would have calculated. But reason what happens here is that the lower the fuel, the much more they're much more probably it can be masked by the cations. That's why it's much lower here. Here it seems to have an opposite effect at 3 and 6. If you look at the 3% here and the 6% here, they actually go up a bit. But when we get here to the boil again, this is a number. I just used 212 degrees here, and there's no way to know. I'm just sort of making this up here, but again, it's just for illustration purposes. And I came up with a calculation of 8.65, which again, if you look at it, it's only about 28% off. Now, with that being said, again, practically, if you had 8.65% fuel in your engine oil, or even if you had 12% fuel in your engine oil, you would be having some severe problems most likely, and would need to have, go have that car checked out no matter what anyway. So whether the number is accurate or not, the practicality of the number that they're putting out, in my opinion, is still viable and good. Now, here what we did was I based the flashpoint here on what did I base this in here on? Oh, I based this on the now I readjusted instead of using 385, because again, they take 385 and they subtract whatever new flashpoint they got from that, and then they multiply that times that'd be divided by 20, and that'll give you the fuel dilution there. So I used a 415 in this case here. Let me show you what I mean. So I use 415 as the instead of 385 for the standard flashpoint, and they do improve a bit here at the bottom. I did come up with 1.5, and again, that is just with me using 0.75. These right here do elevate a little bit, and the 12 seems to be, again, the 12 I also made up, tend to get a little bit better, but they're still quite far off. But again, these I guess the way I'd say this here, I would rather for my data to be overrepresented in terms of fuel dilution than underrepresented. So in other words, if I had 3%, if I actually literally had, let's say 6%, if I literally had 3% or 6% gas in my engine oil, I'd rather for them to tell me it's 9.5% to set off an alarm for me to do something and get active about it, versus the report that is 3 or 2 or 3, because I may not do anything about that. Now, the last one that we want to talk about. So what about refining it to what the SDS says? So let's take a look at the SDS right quick. Give me a second here. So the SDS for this restore and protect here, this is for the 5-quart jug here. All you got to do is look on the back of your restore and protect, and you can get this product code, and you can go to Valovline's website and look up SDSs and put in this code here, and you can find it. So let's go down to section 9 here. Section 9, and this is Cleveland Open Cup, and I do notice it doesn't say it on this one, but there are other variations that actually say Cleveland Open Cup right below it, and they all have the same temperature, by the way. So what about we just use 394? Because I mean, if you can't really use the maximum, you can't really use the middle number, so it's just better to use the minimal number. So in other words, instead of using 385 to calculate our flashpoint difference, those 20-degree drops, we're going to use 394. And using 394, it doesn't really, change everything a whole lot in terms of what I want to say, accuracy. But again, if you look at this one right here, this is I didn't put this out here. This is 1.53612. If you look at it 3%, that's still 3. And they're reporting 3.95 if they were to use that number. So again, not that much of an improvement over Blackstone. In fact, Blackstone's were closer, in fact. So Blackstone values were actually closer. If you look at 3.5 and 8, they were actually closer to 3 and 6 than actually using the SDS. So therefore, the two questions we wanted to ask was, does the 20%, I mean, no, not 20%, the 20 degree per 1% of fuel dilution, does that fact need to be changed? Based on what I see here, I don't think so. I think it's totally fine. Is it the most accurate numbers that it's putting out? Well, if you're going by percentages, no. But in practicality, I would say that they are more than adequate. The second question is, should you use a different base number other than 385? They use 385 flashpoint as their base to calculate everything off of. Should you change to 385? Well, not really. Again, if you look at these numbers here, again, everything goes up no matter how you look at it. And I guess let me backtrack a little bit to the 20-degree drop per 1 degree difference. Sorry, hold up. 20, hold up, 20-degree drops per 1% fuel dilution. That's a mouthful to say that. But I would say that because the numbers here have a slight inconsistency, no matter if you change that factor to something else, that you're going to make some other values like more off than others. What do I mean by that? If we look here, this is this is Blackstone's calculations here, 3.5 and 8, right? These numbers are pretty close to the actual fuel dilution. So if we change this to say every 15 degrees, the number would actually go up. And if you change it to something higher than 20, they would both go down. So but if you change these to go down right here, guess what? The ones up here that's on the low end, like this 0.75, they're actually going to go down. So that's going to be misrepresented. So should they change? I mean, not them. I'm not saying what they should do, but I'm talking about, could somebody reasonably change this? I mean, you got to look at it like this. If you're at a very low amount of fuel, whether you actually got an actual hard number or not, it's not going to matter. But if you did increase that number to say 22 degrees, I'm just making a number up here, it might refine these numbers in the middle range better. But don't forget, this test can only measure up to 10%, then it fails. And apparently, once it get down to around 2, it gets a little flaky. So in other words, from say above 2 but less than 10, the test, let's just say 9.5, just to stay away from 10. Let's say 2 to 9.5, that's a 7.5% spread. So remember between that. So in the middle of the curve would be about 5.75, something like that. So in the middle, you would probably want it to be more accurate, but on the lower ends, doesn't really matter. And on the higher ends, well, you can say it doesn't matter because if you had severe fuel dilution, you're going to have some problems no matter what. They could say, for example, if they said 8%, 9%, 10%, 11%, or 12%, your car would probably be misfiring, probably be smoking, you'll probably be running really rich, you probably have a check engine light. And so either way, you still be within the ballpark of knowing that your car needs to have some attention to it. So with that said, that was the first question. I mean, I had to backtrack on that. And then the second question was about the 385 getting changed. Well, actually not really changing the actual standard, the standard should be temperature. So in other words, let me go back and show you what I'm saying here to make sure being clear on that. If you look here where it says value should be, it says your flash point should be higher than 385. So they use this right here to calculate, to subtract the flash point value from that and then calculate your fuel percentages. So for example, if you look here, if you subtract 315 from 85, you're going to come up, that is a 70-degree difference. So you divide 70 by 20, that's 3.5. So that means you have 3.5% fuel dilution, and that's for the 3% example there. So if you change this number here to 394 or some other number, will it really make a difference? Well, it's the same argument you're making should you change the actual multiplier value. And I argue that changing anything is not going to really affect anything except for if you're trying to refine the middle point of the range, because that's where in the middle point is going to be the most important, because that's when you likely start having problems with your car. On the lower end, say 2 and lower, if you had 2% fuel dilution, 1% fuel dilution, you might not even ever know it actually if you didn't do oil analysis. So there's that. All right, so let's go back and take a look at these graphs here real quick. Just give for people that like visuals, and I like visuals as well. Here's the fuel percent effect on the additive packaging. As you can see, at 0% on all cases, all the way over to 12%, it drops. If you just look at the trend, it goes from this sort of this blue, this navy blue, over to this magenta. Just look at that. That's sort of a downward slope. That's a downward slope here. It's a downward slope for the magnesium, downward slope for phosphorus, and a downward slope for zinc. So it is convincing that fuel does affect your additive package. But the good news again is that the additive package is quite robust. So if you have severe fuel dilution, rest assured that, well, at least I believe that your additive package still will be helping protect your engine. Now, viscosity, just a real quick look at viscosity right quick. Let me resize that just a bit, sort of fit in the screen good here. Wait a minute. Give me a second here. Oops. Give me a second. All right, there we go. So looking at fuel effect on viscosity, you're looking at this. They have 2 different types of viscosity here, 212 degrees Fahrenheit and 100 degrees C. They're about the same temperature. Just this SUS. I should know what that's for. That's slightly below boiling. This is at boiling right here. But the trends absolutely mirror each other in any case, at least in my samples it did. So this is 1, 2, 3, 4, 5 samples, and they all mirrored each other in terms of just trend. So again, pretty interesting. And one last thing I'll say before I head out is that no matter what, you still have to take viscosity into account when you're doing this Cleveland Open Cup. I believe you do, because again, I go back to the example. If your fuel, say if you just done flashpoint testing and your, I don't know, flashpoint dropped to say 320 degrees, but your viscosity stayed within specification, could you or could you not say that's fuel dilution? Well, I would say probably not. So anyway, that's it, guys. That's the study there. I hope you guys enjoyed that one. This was really cool for me to do this because again, this is sort of along the lines of things I actually do in real life for work, except for some more some biological, biochemistry, biotechnology centered. And as you see, things that I do here, this is sort of insight into the reports that I have to write on a daily basis. This is not really a real report here. This is just sort of some sort of insights that you might see on a real report. They're much more complicated than this, but sometimes you got to write methods, protocols, method qualification reports, sample analysis reports, and all sorts of things. So anyway, I hope you guys enjoyed this one again. This was awesome. And if you got any questions, you know I love hearing from you guys, man. Just put it down in the comments and let's talk about it. See you guys later. Bye. Oh, real quick, guys, I also forgot to mention that here's some more resources in case if you want to learn some more about flashpoint testing and all of that. So this right here is the actual ATSM D92. This is the Cleveland Open Cup method here. Of course, you can't read it. I mean, well, you had to pay for it, but again, at least it gives you some information here. Another good resource here is actually Blackstone for February 2025 wrote a nice newsletter about fuel dilution. Do check that out. I swear this thing is quite interesting. I'll just scroll really quick to show you just some quick, like they got all sorts of information and data and things in here. So go check that out. I think you enjoy that one. This article right here is a good article here. This is from Precision Lubrication right here. Here's another one on FTIR here from Machinery Lubrication. And another one from Machinery Lubrication right here is also another good one dealing with FTIR. And finally, this right here is not about engine oil, but it's about testing gasolines. If you really want to go this far with reading, might be quite boring to most people, but this is about gasolines on the FTIR testing. I read this just to see was there anything related to engine oil analysis, and not in the scope of what we were talking about. So anyway, if you're interested, if you have access to such things as these articles right here, this is another good one. So anyway, guys, that's it. Take care.